hardest thing to do, so that won't be happening.
I accidentally did it.
Me and Sai got into a tussle. He went flying.
No.
He went flying. You're just gonna throw him?
Wouldn't be good. All right, properties of logarithms. Today should roll along pretty doggone fast because if you have watched that extra credit video about the properties of logarithms, this is just going to be a lot of use of those. So logarithms are one of those things that have been around for a while. And what we want to do is realize that they came from a necessity of trying to figure out things about exponents, trying to figure out what's going on with all these exponential functions. So we want to prove the properties of logarithms algebraically. We're not going to do a ton of those. We'll do one together, maybe do one in your homework. And it's an algebraic proof. It's not a proof from geometry. We're going to use the properties of logarithms a ton. We're going to talk about expanding and condensing those. We're going to use the change of base formula, which really we've already started to use. And then we're going to graph logarithmic functions of base b. Hopefully we'll get to that today. And then this last piece will be tomorrow, and that's re-express data when seeking a model for the data. And that's because sometimes we get really large numbers, and we need a way to express them so they'll make, well, quite frankly, they'll fit the graphic calculator. The big, huge numbers, the graphic calculator kind of runs scared and does scientific notation. So if we want to do regression with that, we use natural logs in order to get them down to where they're workable. So logarithms have special algebraic traits that historically made them indispensable for calculations and still make them valuable in many areas of application and modeling even today. Again, really large numbers, really small numbers, logarithms work great.
What does indispensable mean?
We can't do without it. Reminder, logarithms are the inverses of unknown exponential quantities. And whatever we do in math, we have to be able to undo. It's always a forwards and backwards process. In fact, if it doesn't work that way, then basically it doesn't get used. Math is one of those things where we always want to make sure if we can do it, at some point we can undo it. So therefore, we use the properties of exponents for logarithms as well. So what does that mean to us? It means this. If you know how to do that, you really learn how to work with logarithms. Because we have the same base and we're multiplying, we add the exponents. So in logarithm language, multiplication is really addition. That's one of the properties that we have. One of the properties that we just used with the decibel examples told us, hey, if we're going to divide similar bases, we have to subtract the exponents. So division in a logarithm language is going to be subtraction. And then we learned when you raise a power to a power, you're supposed to multiply those exponents together. So in logarithm language, when we raise something to a power, we're going to use multiplication. So these are not new properties to us. It's just it feels different when you use these for logarithms than it does for bases with exponents. So basic properties of exponents right here. Multiply similar bases, add. Divide similar bases, subtract. Power to a power, multiply. And we see that that's really what logarithms are doing here. If we were going to multiply the logarithm base b of r times s, we could use addition. Logarithm base b of r plus logarithm base b of s. Logarithm base b of r over s, well, that's division, and that's subtraction in logarithm language. And then here we see the logarithm base b of r to the c power. Remember, powers to power means multiply. So we bring that c out in front and we multiply by it. So we've got the product rule, the quotient rule, and the power rule. And it says, notice that the first property of exponents is used to verify the product rule for logarithms. And we're going to go through a proof here. And proofs, remember, work this way. You remember from geometry. You have to use prior knowledge, things that you already know work, in order to prove something. And in this case, that would mean we're not going to be able to really use logarithms to prove this, because our prior knowledge before we learn about logarithms is exponents. That's where it comes from. So when I look at this and think, okay, I can't use logarithms for this, so maybe I'll just by starting to say that x equals logarithm base b of r, and y equals logarithm base b of s. Okay, not supposed to use logarithms to prove logarithms. Well, I could snail shell. I mean, I can do that. So I've got x equals logarithm base b of r. That would be b to the x equals r. And this one would be b to the y equals s. Okay, now what am I trying to prove? I'm trying to prove that if I multiply these two together, it'll really be addition. So let's see. If I multiply, bless you, r times s, oh yeah, it will be addition. Look at that. Now let's see. I did what I was supposed to do. Oops, forgot to put the plus in there. I did what I was supposed to do, but it doesn't look like this. That's all I have. Okay, so let's see. How could I get it to look like that? Well, I could take the logarithm of both sides, logarithm base b. Something cool happens over here. What happens on the right-hand side when we take logarithm base b? Remember I started by substitution because I couldn't use logarithms all the way through the proof? I didn't use logarithms through the proof. I just took logarithms right now and I substituted for x and y. So let me put back in what I had for x and y up here. Logarithm base b of rs equals logarithm base b of r plus logarithm base b of s. By golly. That's what we're supposed to have. So we use what we know about exponents and say, this is how it's supposed to work. I know this about exponents, but I can't use logarithms all the way through the proof because all I know about is exponents. Do what we can with the exponents, and then at the end, take the logarithm and put logarithms back in. Because we're not doing any math with the logarithms here. We're just simplifying with it. And so we're okay. It's back in there. That's what we need. Now, back in the old days, you know, when dinosaurs roamed the earth and I was in high school, we didn't have graphing calculators. In fact, nobody had calculators. They were too expensive. You never bought a calculator. It was calculators like that just did addition, subtraction, multiplication, and division for $30. Nobody bought a calculator. So what we had to have was in our book, there was about another half a book worth of tables that had logarithms in it. On paper, they had calculated logarithms and they were in the back of the book. But it wasn't every logarithm you would ever need. So you had to figure out how to use the properties of logarithms along with the table that was in the back and the numbers that you had. Let me give you a for instance here. If we had the logarithm of 2, we could think of ways to figure out, well, basically we could think of through like the logarithm of 2 squared, which would be 4, right? But how we would do it is we would say, well, raising things to a power with logarithms, that's multiplication. So from the back of the book, in this table, we had logarithm of 2. We could use that for any powers of 2 and figure it out. And then, see here, we've got a logarithm of 4. Well, now we can do any of the powers of 4 that we would need and different things. For instance, maybe we could say, I want the logarithm of 4 divided by 2 if we didn't have the 2. That way we could get the logarithm of 2. But it would work really awkwardly because we'd have to use it to get it itself. So that wouldn't have been a way to go. We could use logarithm of 16 divided by 2 to get logarithm of 8. There's all kinds of properties that we could use along with that table. And that's what this little box here is trying to get across to us is, just because you didn't have your graphing calculator with it doesn't mean you can't do some of these problems. In fact, when these have shown up on the ACT, usually they give you the logarithms that you're supposed to use to find these. So it says Use the 5 decimal place approximations shown in figure 3.26 to support the properties of logarithms numerically. Logarithm of 2 times 4. Well, that's logarithm of 8. So instead of punching logarithm of 8 in, you say, well, multiplication is addition in logarithm language. And I've got to be able to see that table. That means we're going to add 0.30103 plus 0.60206. And if we do that, we should get the logarithm of 8. So we add those two things together. I don't know if you'd want to use a calculator or not because these are nice and lined up, but just to show everybody up there on the big old screen, 0.30103 plus 0.60206. And we get that. Look at their little graphic calculator display. That's the logarithm of 8. So if you didn't have the logarithm of 8 available to you, you can still find it using log of 2 and log of 4. This one says logarithm of 8 divided by 2. Well, that's really log of 4. But let's just say you didn't have log of 4. You had log of 8 and log of 2. Division is subtraction. So you could go up there and say, all right, I need 0.90309 minus the log of 2, which is 0.30103, and you would not be shocked to find out that it is 0.60206 using the properties of logarithms. Power property. Logarithm of 2 to the third. I already kind of touched on that with my 2 squared over there. This is a power. We bring it out front and we would multiply. So we could take 3 times 0.30103, and again, we would not be shocked that that equals the logarithm of 8. 0.90309. Now, I mentioned the fact that we had to use the tables because what those tables did was they forced us to use powers, multiplication, division in our head and get number sense about what combinations of numbers would work. So it says now evaluate the common logarithms of other positive integers using the information given in figure 3.26 without using your calculator. So I start thinking, we've got log of 2, log of 4, log of 8. And since we're using common logarithms, one of the other things that we would use a lot would be log of 10. How come? It's 1. So we're supposed to know that one. You know, it's not like they're giving us new information because the bases match. That's going to be a 1. So when we look at this, it says use the fact that 5 equals 10 divided by 2 to evaluate the log of 5. So what are they really telling us to do? Instead of using log of 5, what would we do? Some subtraction. So we take 1 minus the logarithm of 2. If we can't use our calculator and it's not available to us, do some subtraction. This one says use the fact that 16, 32, and 64 are powers of 2. Well, that means we'd be using log of 2. How would we get log of 16 to be something we could use as log of 2? Is 2 to the 4th. So 4 log 2. How about log of 32? 2 to what power gives you 32? Out loud would be nice. 2 to what power gives you 32? 5. 5 log of 2. 64. 6. Yeah, 32 times 2. 64. So we wouldn't be able to give up. We would have a way to do that. Hi, share your delivery. Thank you. I appreciate that. Thank you. Bye, you too. All right, using 2, 4, 8, and 10. It says, how could we figure out logarithm of 25?
Figure out 5. Number 4.
What are you doing, Art?
Well, you figure out log 5 already, so if you then make that 5 to the second, figure it out.
Oh, so you're saying kind of cheat and go back and look at what you already had for number 4 and multiply it by 2? Absolutely, we can do that. We've already calculated 10 divided by 2. We can do that. How about 40? What could we use for 4? 4 times 10, so we could add them. Log of 4 plus log of 10. Okay, how about 50? You could go back and you could use the 5 up here. What would be another way to get the 50? You could do that. You could use this one from in front. Well, yeah, we could just add that. We could add the log of 2 because 2 times 25 would be 50. Yeah, we could do that. So you could use one of your previous answers. So this last part we're not going to focus on. But this is about just manipulating, using what we know about the properties that we have for logarithms to make things work. And yeah, there's all kinds of spots down here, but like I said, if you watch that extra credit video, the properties will start coming to you. When we solve logarithmic equations algebraically, we often have to rewrite expressions using properties of logarithms. Sometimes we have to expand, and sometimes we have to condense. So expanding means we're taking these and we're stretching them out into a big long list. We're separating any multiplication into addition. We're taking any division and we're changing it to subtraction. And we're taking any powers and we're changing it to multiplication. So that's expansion, making that happen. And when we condense, we pull those big long statements back into one logarithm statement and just get the one condensed form. So this one says we're going to expand the logarithm of a product. Assuming x and y are positive using properties of logarithms, we're going to write logarithm of 8xy to the fourth as a sum of logarithms or multiples of logarithms. Okay, first of all, is that power of 4 for everything that we see up there? So we can't start there. We have to start by separating this into things that are separatable. You know, this x to the 4th or y to the 4th is not for everything. So multiplication in logarithm language is what? Addition. Log of 8 plus log of x plus log of y to the 4th. Now there's no division here, so I don't have to worry about changing anything that was division into subtraction, but I do have the power, and that power is multiplication. So log of 8 plus log of x plus 4 log of y, and it's only with that term because that's the only one that had the 4th power. That was it. Let's go to example 3. Expanding the logarithm of a quotient. Boy, I can't stand the way that's typed in there. Like so. As the sum of difference of logarithms or multiples of logarithms. Now I need you to pay attention to something. The square root up here, it's not parentheses, but it is grouping symbols. A square root is considered to be a grouping symbol. That means we cannot separate this x squared plus 5. Those two things have to stay together. But what would you do first to separate this stuff? Subtract. So we've got natural log of the square root of x squared plus 5 minus the natural log of x. Kevin, pay attention. Now what? Change this to a fraction power. So that we can do what? Put her out in front and multiply. Now here's where people always have trouble. Should we be separating that x squared plus 5? Nope. Remember, these were grouping symbols. That grouping has to stay here. So we're not going to separate the x squared plus 5. We took care of the division. We took care of the power that was there. It's expanded. That's what we could do with that one. Now let's condense. So now you need to think opposite. Put the powers back up. Then anything that's added was multiplication and anything that was divided was subtraction. So do we have a power to put back up? What does it go to? Both the x and the y, because there's parentheses here to show us. This came from up here. So natural log of x to the 5th minus natural log of x squared y squared. Where's the subtraction coming from? The division. Notice how we just have one natural log statement. And with this one, we can go a step further and we can do some simplifying. Take a couple of x's out of there. Basically, we're just canceling, or you can think of it as subtraction. 5 minus 2 is 3. And that'll give you x to the 3rd. So that is condensed. Condensing is important when we want to solve logarithmic expressions, because in order to snail shell, we have to have one logarithm statement. All right, x tree examples down here. How are you going to write natural log of 3 times 5? Nope. They want us to separate this using properties. Plus, yep, multiplication is addition in logarithm language. B needs to be expanded. How? Lots of addition. Got everything being multiplied there, so that's going to be addition. C is a condense. Take a look at the operations they want us to do. What do those operations mean? Multiplying. So we're really supposed to put natural log of 4x times 3x times 2. Well, that we can do. 4 times 3 is 12, times 2 is 24, x squared, and then I probably would put parentheses around that so that people know, hey, this stuff was all together when we started here. But that's the condense. So expand and condense, definitely necessary. Like I said, the condensing we're going to use a lot for solving logarithms. You use the expanding quite a bit in calculus to get it into pieces of natural log that are workable. So if we expand natural log of 4 over 3, what do we do to it? Subtract. What's the major thing? Division, and division is what? What do we use for division? That one's not done. Yeah, so the problem is, right now, we're saying, hey, this was division. So really, it's almost like there were parentheses back there. So we could write it natural log of 7 minus parentheses natural log of 6. Thanks, Miss P. Oh, well, that's not helpful. Wait a minute. You get more than one. I'll take it. But when you expand, you want to get rid of any parentheses that you can. So the question is, would this get somebody back to that? If you follow the order of operations, sure it would. You're supposed to work left to right. So you'd say, oh, here's my 7. Oh, got to divide by this, and I have to divide by this. So we want to try to get rid of as much as we can when we're expanding. All right, we got a little condense action here. It looks like there's a lot of subtraction going on. Huh. So what's all that subtraction business for? All of it's division? So what are we supposed to put on the top? 3 times 5 is 15, x squared. That's going to get all of that division taken care of for us there. How about expanding 2 to the 3rd? That's a little silly, but what would we do if we're using that power property? Multiply. Natural log of x squared? Condensing again. What do we have to do first? Yeah, put those powers back up. So now the powers are back up. What do we do? Okay, we've got multiplication here. But what's the minus for? Division. And now we've got one natural logarithm. Oh, that's really tiny. You're supposed to know what that is just by looking at
X squared.
it. You could, well, hang on. You could do it that way. You could do it that way. Put it back up right away. Most people would probably just drop the ln first and then put it back. But yeah, all right, you got it. That's probably going to work best. Alrighty. I don't necessarily need you to be able to do this in one outing. I mean, look at that problem. Yikes, right? But if we can get it there, that's what I care about. So, pieces. Start with something. What do you want to do? We should really do numerator first. So that stuff on the top there, what's going on with all the stuff in the numerator? In multiply. So log base 7 of 5 plus, but it's going to be log base 7 of x squared, and we're not supposed to leave the 2 there. So what do we do with that? Bring it out front. And now we need a power. This is being squared, but then it's a third root. 2/3. Should we be ripping apart that 2y minus 1? Nope. All right, now we've got to do some division, so that's going to be subtraction. Logarithm base 7 of 2. Now you make a decision. Do you want to use parentheses right away, or do you want to just go for the answer? Okay, then let's put subtractions all over the place. Minus log base 7 of 2, minus log base 7 of y, minus, what are we going to do with that square root of x plus 1? 1/2. Should we rip the x plus 1 apart? No. In the original, those were together. There it is. So, when you get there, you can just do all this in one step. Again, I don't need you to be there today. You know, we're going to take this in steps. This one, let's try and condense this all at one time. So we want natural log something. What are you going to do first? Okay, so let's put this 3 back maybe. Maybe as a -3 even. So that'll be 1/8. Minus 1/2 natural log of x. 1/2. Where'd that come from? Square root of x. Does it go on the top or does it go on the bottom? Bottom. Next one has addition. So where's that going to go? On the top. But it's going to be 3x squared. So what's that going to give us? 9x squared. Does the last one go on the bottom or on the top? Top. Now again, they wanted us to do this in one swoop, so they were hoping we'd get here and go, wait a minute, that's going to be 18x squared y squared. Again, I don't need you to be able to do it in just one step today. Because at this point, of course, we would want to condense this even further. What are you going to condense? The 18 and the 8? And again, that might drive some people nuts because we've got a square root in the denominator. So at this point, maybe you would switch to fraction exponents and try to condense it even further. But generally, when we condense, we do leave square roots in there. So we could stop right there. And that's just using all of those properties and our knowledge that addition is multiplication, subtraction is division, and when we see those multiplication pieces, that came from a power. So logarithms have some surprising properties. We need to be able to decipher what is true and false about logarithm relationships. So expect some true and false questions in your homework, but we're going to look at a couple right off the bat here. Don't be impulsive. That's always the problem with true and false and multiple choice. I want you to think through these answers. It says we've got 8 of them. 4 of them are bad, 4 of them are good. Number 1, the natural log of the quantity x plus 2 equals the natural log of x plus the natural log of 2. Good or bad? Bad. This is supposed to be multiplication in order to be addition. That's not working. Look at number 2. Logarithm base 3 of 7x equals 7 logarithm base 3 of x. True or false? Gonna work? Multiplication is supposed to be addition, isn't it? It's not about powers. Take a look at 3. Logarithm base 2 of 5x equals logarithm base 2 of 5 plus logarithm base 2 of x. True or false? That's one of our properties. Number 4, natural log of x divided by 5 equals natural log of x minus natural log of 5. True or false? True. One of our properties. I suppose I could just continue with my T and F. Number 5, logarithm of x over 4 equals logarithm of x divided by logarithm of 4. Yes? No? Maybe? False. But it's division and this is division. What's division supposed to be? Subtraction. See, that's that impulsive part. You start to think, wait a minute, that should work, right? No. Logarithm base 4 of x to the third equals 3 logarithm base 4 of x. True? One of our properties. Bring this 3 out in front. Number 7, logarithm base 5 of x squared equals logarithm base 5 of x times logarithm base 5 of x. False. It's not one of our properties. Number 8, logarithm of the absolute value of 4x. Ooh, we haven't even talked about that yet. Equals the logarithm of 4 plus the logarithm of the absolute value of x. What do you think? It's going to work, isn't it? It takes the absolute value where it needs it, which is with x. And we've got multiplication, that is addition, in logarithm language. 1, 2, 3, 4 truths, 4 falses. So there they are. So again, don't talk yourself into believing everything they're doing when you do the true or false questions. Think through what are our properties, the ones that we absolutely know. So although some of you have calculators which allow you to change the base of the logarithm, we talked about this before. Some of you, when you hit logarithm, you get a little box for each one of those, so you can change the base. Most of us don't. Most of us are not going to have those. Those are the newer calculators. So we're going to have to use the change of base formula, and it's something you have to know how to do anyway, because a lot of college classes require that you show the work when you go through and use the change of base formula. So most of us don't have it. Some do. The newer ones do it. But we want to evaluate the logarithm base 4 of 7. So the first thing we could do is use algebra and say, well, bless you, 4 to the y equals 7. Well, 4 to the first is 1, and 4 squared is 16. And it's somewhere between those two. So we could sit here for quite some time and try things up there with the graphing calculator to make that work. but we're just wasting time because we have the change of base formula. And the change of base formula says take the logarithm of the number you're trying to evaluate and divide it by the logarithm of the base. And in fact, it doesn't matter if you use common logarithm or if you use natural logarithm. And because we'd like you to get a little more comfortable with natural logarithm, we're going to try to get you to use natural log more. So when we punch this in, as long as you can get the right answer on today's, that's okay. But again, we hope everybody starts to get a little more comfortable with E. So there's our answer. And again, with logarithms, we usually do 4 decimal places. It's just, it's been done that way for hundreds of years, you know, so generally you're going to see 4 decimal places. And once again, they inform us down here, the change base formula says it doesn't matter what the base is as long as you use the same base for both of them. Logarithm base A of x, logarithm base A of b. So you can use log for both of them, or you can use ln, log base e, for both of them. Just don't mix and match. It has to be the same for both. So you put the logarithm of the base in the basement, 2 B words. The logarithm base is always in the basement. And these are obviously the 2 most commonly used because they're on the calculators. You know, we don't have to use tables or anything. We just got a calculator, you punch them in, and all is good. So now, evaluating logarithms by changing the base. Yeah, this is going to be kind of silly, but let's go ahead and do it. So, just to get you feeling a little bit better about natural log, let's use natural log. What's going on top? 16. Base is in the basement. We grab the good old calculator and we see what it tells us. Natural log of 16 divided by natural log of 4 decimal places. 2.5237. Got it. Natural log of something over natural log of something. What's the something for the top? Which one goes on top? Natural log of 10 divided by natural log of 6. 1.2851. Rounding to 4 decimal places. Oh, I don't think we need a calculator for this one. Do we? Maybe we do. Big snail shell. So we need to recognize that we don't always need a calculator. You know, take a look at it quick and say, yeah, I don't need the calculator. This is going to happen. So down here we have graphs of logarithmic functions with base b. Using the change of base formula, we can rewrite any logarithmic function as, look at that, like graphing logarithms wasn't already intensive. You know, a lot of steps that we were looking at. So now they're saying if you're forced into using natural logarithm, think change of base formula. Think, how would I write this as a change of base? And then realize that this natural log of x is a parent function. So if we rewrite it as 1 over the natural log of b, that's going to be a vertical stretch or shrink, depending on what our numbers come out to be. With our current bases being greater than 1, then this is always going to be a vertical shrink of 1 over natural log of b. Therefore, every logarithmic function is a constant multiple of the natural logarithmic function, which means we could use natural log as a parent function. If the base is greater than 1, the graph of logarithm base b of x is a vertical stretch or shrink of the graph. F of x equals natural log of x by the factor 1 over natural log of b. When the base is between 0 and 1, which is going to be basically fractions, well, those would have negative powers. And so that would give us a reflection across the x-axis that would be required there as well. So, let me talk you through this one. It says, describe how to transform the graph of f of x equals ln of x into the graph of the given function. Then sketch the graph by hand and support your answer with the grapher. So what they're doing is they're forcing us to think natural logarithm. So when I look at this, I'm thinking, okay, well that's not a big deal. G of x would be natural log of x over natural log of 5, because if I had to punch this into the calculator, I would use the change of base formula. So what they want me to do is say, here's the number in front that would be the stretch or compression, and then put this ln of x in the back, so I can kind of see that as a parent function. Well, it would be 1 over natural log of 5. And they want me to describe what that's going to do. Well, e to the something is 5. That's going to be a positive number. So 1 over a positive number, that's going to be a fraction between 0 and 1. This is going to be a vertical shrink factor 1 over natural log of 5. So, bless you. You just kind of do that little snail shell in your head real quick and say, e to the something is 5. Okay, well, it's 2.718, blah, blah, blah. So it's going to be more than 1. Oh, that's going to make this a fraction between 0 and 1, which makes that a vertical shrink. But I'm not graphing this the hard way. I don't know about you. I'm not going to graph it with ln of stuff when we could just snail shell it and graph backwards. We did what they asked. They said, how would you transform this? Boom, there it is. But if I'm graphing this, I'm going to do 5 to the y equals x and just get it done. You know, I'm not going to spend all my time thinking about what's e to the first again, what's e to the second again, and all of that. So we put in some numbers, -1, 0, 1, and 2. Maybe would be good enough there. And we'd say, hey, the whole process is backwards, but if I put -1 in for y, I'm going to get 1/5. If I put 0 in for y, I'll get 1. Put a 1 in and I get 5, and 25 gives me something to shoot for. And that would be my graph. So 1/5 -1, 1, 0, 1, 2, 3, 4, 5, 1, and 25, 2, I'm just going to aim for. Rather than graphing natural log of x, which would be e to the y equals x, and then trying to perform a vertical shrink of 1 over the natural log of 5. No. I can describe it, but I can graph it however I want to graph it. And that is the choice I would make for graphing. Good. It is. It is, just like any of our logarithms, right? All right, so describe the transformation, did this. Oh, did they say to do anything else? Describe how to transform, sketch the graph by hand, support your answer with the grapher. Oh, well, we definitely could punch it in at this point. And see that it matches. You know, just use the change base formula. Let's do that. I guess we haven't done that before. Graphing using the change base. So we'd have natural log, I'm going to use parentheses here for the top of this. Natural log of x numerator divided by natural log of 5. So since there it is, no shocker. And that's what we got when we did our little snail shell there. Are we getting close? All right, well that's not too bad. I had hoped we'd get through both of these graphing ones, but you know what? That's not too bad. So our objective covered a lot of stuff. It really did. And we had talked about in this section, we're covering a lot. And the one last thing, the one last piece of our objective that we don't have is going to be that we express data when seeking a model for the data. But we proved the property of logarithms algebraically. We used the properties to expand and condense. We used the change base formula, and we did one graph. So we are well on our way. And I remember this one going really, really fast. Oh yeah, this is the properties assignment. Yeah, this goes really, really fast.
This one, I don't know how you get x squared to that.
Yeah, you see this. This 2 is multiplication for the k to the power. Now if we add this e, this is really logarithm base e. Just wait. See what base is.
Yeah, but you can cancel, you can cancel out with that.
Oh, ln is the same as log base. Change from log base, whatever, to.
Oh, because that's, if somebody doesn't see it, I just always write it that way, so that you can see the two e's, two of the bases. They are exactly the same thing. ln and logarithm base e are exactly the same thing. I know. There's an e there.
Yeah, so if you write it, that would be a fraction to the right.
This.
Yeah, that.
Okay.
Well, everybody will perform this week.
Have a great day.